you just get so excited about the project that you want to work day and night and all weekend long. And that's, of course, the only way you can ever get a PhD is by doing that for an intensive burst of time. So.
Yeah, exactly. PhD is a 4 year, at least 4 years or 3 or 4 years. So, I mean, it's kind of challenging to really achieve like a deeper research project if you do not have interest. So, just add. I hope that it can bring something interesting for my PhD students.
Well, and I know we have some what we call future students here, which are students who might be in high school or middle school or grade school. And so the way college works is, so first of all, you got to kind of graduate from high school. So high school is grade 12 in the US. And then after grade 12, there's 4 more years in which most people can earn their Bachelor of Science or their Bachelor of Arts degree. And so all of the engineering degrees and nearly all of the science degrees are Bachelor of Science degrees in something. And so, for example, Dr. Sun works in the Department of Mechanical Engineering, Engineering Mechanics, and where they award a Bachelor of Science degree in mechanical engineering. And so in the College of Engineering here at Michigan Tech, we have 16 different degrees in the College of Engineering alone. And then across the university, there's another, gosh, I can't even tell you how many there are. There's lots and lots of bachelor's degrees here at Michigan Tech across all kinds of fields, from forestry to business to computing to, archaeology. There's all kinds of interesting degrees. So that those 4 years after high school, that's where you're earning your bachelor's degree, whether it's a Bachelor of Arts or a Bachelor of Science. So then you can be done at any point, right? Nobody's making you go to college anymore, but typically that 4-year degree is something that you pay for, or you have scholarships to pay for part of it or something, but the money is flowing from you to the institution. And then in the technical fields, so engineering, computing, these kinds of things, the equation reverses and they pay you. So Dr. Sarah Sun is paying George likely a stipend in order to do research in her group through one of her 3 National Science Foundation grants that she has to do soft robotics. And so you can earn your master's not only without paying tuition, but you get paid. And similarly, the same thing can happen. So the master's usually takes 2 years, and then what we call the terminal degree, not because it kills you, but because you're supposed to be done at the end of this. That terminal degree is your PhD, which is called your doctorate degree. And that will typically, as Dr. Sun was just saying, it's typically a 4-year degree if you're really kind of focused and working hard. And you can earn your master's in parallel to that, which is what George is doing. George is earning his Master of Science in Mechatronics. At the same time, he's earning his PhD in mechanical engineering here at Michigan Tech. So that's a crash course in graduate school. And I never set out to earn a PhD or anything like that. I'm the first one in my family. But once I got into grad school, I was like, hey, this is a lot easier than earning my bachelor's degree. So I just want to say it is easier because you're focusing on fewer things, and you can, taking 5 classes at once is hard. That's what you have to do for your bachelor's degree. And then once in grad school, you're typically just taking 1 or 2 courses at a time. And the rest of your time you can devote to your research. So I think we're going to get a chance to hear a little bit about George's area of research shortly, and also about Dr. Sun's research area. So we're coming close to the hour. I'm going to kind of just kind of introduce a few topics in general. So welcome to Husky Bites. If it's your first time joining us, I can see we already have 53 external attendees, and we have countless more already kind of watching it on Facebook live stream. Husky Bites is a webinar series offered at Michigan Technological University. I am the host. Tonight joining me is George, who is my co-host, George Ochieze. George is, as I was just saying, a PhD student and a master's student here at Michigan Tech, where he's studying mechanical engineering and mechatronics. He comes from Aba, which is in Abia, Nigeria, and we were learning earlier how he got introduced to this field a little bit through his father's business. And I forgot to ask you, maybe you can tell us later on, George, how you heard about Michigan Tech. And so George is co-hosting with me tonight's featured webinar speaker, who is Dr. Sarah Sun. Sarah comes to us with a really interdisciplinary background. She started with her Bachelor of Science degree at Tianjin University, which is in a region north of Beijing. And she told me it's an area colder than Houghton, which I was just shocked by. I'm like, oh, I'm not sure that's possible, but she says we have more snow, in the winter. Right? And then she went and earned her PhD in the United States and joined us 6 years ago in the Department of Mechanical Engineering Mechanics. And so her area of research is an area called soft robotics, and that's going to be something that we learn a little bit more about tonight. Just a few more words about Michigan Tech. So Michigan Tech is short for Michigan Technological University. We are a comprehensive university that awards doctoral degrees, bachelor's degrees, master's degrees. We are located in the Upper Peninsula of Michigan, and I always do this wrong, but that means if this is Michigan, and the area below my other hand is Wisconsin. This is the Upper Peninsula of Michigan, and we are right here. And so we are surrounded by Lake Superior. It's a very, very beautiful part of the world. Founded in 1885, this university is well known for starting off with training mining engineers, and now there are 16 different degrees awarded just in the College of Engineering alone. So a very brief introduction. My name is Janet Callahan. I'm the Dean of the College of Engineering. I am just going to be with you tonight to help facilitate the conversation. And I have some homework for you along the way. You should invite your neighbors and your neighbors' kids and your, all kinds of people, because this is a great way for them to learn about the different fields that they might be interested in earning a degree in, because hardly anybody knows what they're going to major in. I know I started college without the slightest clue, and I changed my major like 6 times. So this series is a great way for people who don't know what they want to do. And so with that, I want to wait, I got to share screen. And let me do this. And I have a slide I want to show you. So this is our Husky Bytes website. And that's where you can find the latest speakers. And the whole lineup is posted now for all fall. All right, I can never do this. I got to practice doing this offline. So I think this is big enough for you guys to see. So this is the opening slide. I want to make sure that you can see who tonight's sponsor who is Darwin and Margarita Moon. These are available to be sponsored. Do not feel obligated to sponsor one, but if you do, 100% of the proceeds go to support students. So I just kind of want you to know that. If you should happen to lose us, feel free to join in on Facebook Live, and that's another way to refer people to us. I wanted to show you this hilarious slide. I'm not going to reveal this person's name, but after receiving his Husky Bytes t-shirt and mask and wearing his mechanical engineering hat, he sent me a picture, and I said, can I show you this? And so this is one of our alumni, class of 69, mechanical engineering mechanics. And with that, Sarah, I want to turn it over to you. So Dr.
Sure.
Sarah Sun is going to be speaking with us about this general field of soft robotics.
I'm very glad here to have the chance to present some pieces of stories in my group. So I would say that today I make a yard sale right here that I'm going to introduce some interesting stuff in my group. And my group is doing design, more about mechanical and electrical design. So today I'm going to share some devices and share some stories. And so let me share my screen. Okay, can you see that?
Yes, we can. And George, if I ever get dropped or lost, you are the host. So you just got to, feel free to kind of run the show, because it does happen from time to time in the area that you get dropped out. So yes, okay. We can see it. Go ahead and make it the first, hit the slideshow button.
Sure. So I'm Sarah Sun, work in mechanical engineering at Michigan Tech, which I'm very proud of. And so here I have I just copied the small doc here, and which I want to welcome everybody to join the Husky Bytes. Okay, so the topic today I'm gonna present is nice shirt, embroidered electronics and motion powered devices. So which is some projects that we're doing in my group. Okay, so before I start to introduce these stories, I would like to share some facts, and we have some polls there. So chronic diseases cause 7 in 10 deaths each year in the United States. And these examples include heart disease, stroke, diabetes, and etc. So here comes the first poll that, can we pull up the poll? Okay. So the first poll is, what is the percentage of nation's annual healthcare expenditures spent on chronic and mental health conditions? Can you guess? Oh, we see numbers coming in.
So the choices are 90%, 75%, 56%, 34%, or 17%. And so it looks like the majority is going for, I would call that option B, because B is usually the right answer on a multiple choice test, which is 75%. So
75%, okay, 75%. Okay. So
what's the answer?
The answer is 90%. Can you believe that? 90%. So,
well, then only 13% of the people thought that was the right answer, so.
So it means that a large portion of the expenditure is spent on chronic conditions. So here comes to, can I stop the poll?
I stopped it.
Okay, great. Okay, so here comes to a necessary healthcare transformation from hospital-centered to preventive, proactive, human-centered healthcare, which is also promoted by National Science Foundation. So we want to look for technology so that we can achieve human-centered healthcare, which means the healthcare is not necessary to be happening in hospital. We probably can do proactive, preventive well-being management. There are some other facts about human errors. So each year, over 6 million crashes occur on US highways. They kill more than 42,000 people, injure about 3 million others, and cost more than 230 billion per year. So then comes to the second poll. Among them, what?
No, I'm just gonna guess. I'm gonna guess A this time, personally. I don't know about you guys. So go ahead and launch the next poll.
Okay. Okay, the next poll is, what is the percentage of driving fatigue, which is one of the human errors leading to all the fatal crashes?
All right, and the choices are A, 90%, B, 75%. So now they're choosing B. C, 56%, D, 30, same percentages as before, 34, and nobody's guessing 17%. They're way savvier than that. But it looks like overwhelmingly at about 55% level, they're choosing option B, 75%. That was wrong last time, remember?
Okay, do you wanna change? Okay.
All right, so what's the answer?
Okay. The answer is 17%, which is the last one, and it seems like we have 0 there.
Nobody. So nobody. So very, very little. Well, that's interesting. It must be our own clumsy driving then that leads to most of the fatal crashes. Interesting.
Yeah, think about the fatal crashes. There could be a lot of factors, and driving fatigue, which is one of the human errors, is causing 17% of all the fatal crashes.
Okay.
That is also a lot, because think about our crashes, we have over 6 million. So even 17%, that is still a large number. Okay, so can I end the poll? And
Yep.
this data is from the Federal Highway Administration. Okay, so how about the driver state monitoring? There can be some solutions of driver state monitoring. These are just some facts about, okay, the human sensing. So then the question is, what can we do to help the healthcare transformation and also prevent crashes caused by human errors? So then it goes to the solution of us that at Tech, we propose the human-centered monitoring, which is my lab, and we call it human-centered monitoring laboratory. So we couple enabling technology, human factors, and computational diagnoses. And these three needs to be coupled together so that we can provide, and hopefully we can provide some good solutions to solve it. Okay, so personally, I'm passionate about using engineering solutions, especially novel engineering solutions, to help improve the current healthcare and the current driving safety. Okay, so then goes to the health monitoring devices. So here I have an example, which is for the blood oxygen monitoring, and I just bought it from Amazon. And it's kind of for the COVID symptom monitoring. So here we have two polls. Among over audience, do you own any health monitoring devices? And do you say, okay, I buy the thing, but I do not really frequently use it. So do you frequently use these health monitoring devices?
Well, for me, it's yes and yes. And it was a year ago I bought an iWatch, and I'm shocked at how much about how useful it is. Honestly, you know, I go for a walk, I can see my heart rate, I pick up the pace, you know, because I'm like, okay, you got to get your heart rate above 90, Janet, you know, and it's very, very interesting how profoundly this influenced my life. Of course, it also knows everything I'm doing, and I have no privacy anymore, but you know, it's okay. All right, so the poll answers are relative to do you own any health monitoring devices, 77% of people do. And then do you frequently use these? 52% of people do, 35% don't, and for 14% of the people, it's not relevant. And so those might be our future students because they're healthy and they're young. I don't know.
Yeah, for me, I fully understand that because for me, I do wearable electronics. So I have a lot of these health monitoring devices. And also for personally, I bought a Fitbit, but I would say I seldom use it. I use it in the beginning and then I kind of quit. So there are some reasons. One reason that I have is that I often forgot to charge it. So then,
George, do you have an iWatch or anything like that?
No, I don't, but my phone has a sensor monitoring device.
So it's monitoring how much you're walking and all that kind of stuff?
Yeah, but I don't use it that often.
Yep. So it comes to why I have these devices, but I do not frequently use them. So
it's because you're not in your
reason that, which is our work, that we're trying to solve the current existing problems of wearable electronics. And what can we improve to really enable the ubiquitous sensing? We call it ubiquitous sensing because we want all these health monitoring to happen without disturbing humans' life. Say, okay, I can do whatever I want. Say today I forgot to charge, and then it's still okay. I can have it forever. So here are some examples, which here, the yard sale today, what we're doing at Tech. So these are some photos that we have some products in our group. And the first one, which is a non-contact ECG. Why we called it non-contact? Because we do not need any wet gel, and we can have these devices outside the clothes, and we can still monitor the ECG and EEG and EMG, which is the biopotential. The ECG means the heart shape. The EEG is the brain activity, and the EMG is the muscle signals. And we often use the muscle signals as the interface to control robotics. Okay.
Does it have to be touching your skin, or you can wear it?
So for ECG, and we can wear it. So we can wear it outside the clothes, and we can still have the ECG.
Wow.
But for EEG and EMG, because the amplitude is pretty low, means the signal is very weak. that's kind of hard to capture outside multiple layers of clothes. So later I'm going to show it. So the next one is a flexible ECG, which I'm going to talk about today, and the nest shirt. And we call it embroidered electronics, that we make everything on the clothes, and we can still use it to, we can still do the signal acquisition, and we can still have the ECG. Okay, and the next one is still based on, we call it embroidered electronics technology, and this is a GSR. GSR means the skin conductivity. And we also have the motion sensing products, and this is a self-powered motion sensor, and this is a variable joint motion detector. And these are kind of some products I want to show. So I name it as yard sale because I want to tell some stories, and I hope that you are interested. Okay, and George is going to tell some other stories, which is some new direction in our group, which is the soft robotics, and he has some videos to show there too. Okay, so everything is for sale today. If you're interested, just contact me. Okay, so it goes to the textile, and which is we call the embroidered electronics project. What is that? So now we have these devices, we have Fitbit, we have iWatch, we have everything that is kind of on the hardware. So how about we enable everything on our clothes? So we have so here we have some examples. This is an antenna, which is a fabric antenna. And it can do the wireless communication, but we do not really need like a regular antenna. And this antenna is being embroidered on the clothes. And there are some examples on clothes, and they can detect different type of vital signals. And also here is one example of the keyboard, a embroidered keyboard. And so what we can do is, how about we integrate here we have a embroidered logo of Husky cat, of the little Husky dog, which is right here. Okay, so how about we integrate it, and we can do what the embroidered electronics as what we want. So for example, today I want to have a ECG monitor so that I quickly do a broadery of the ECG monitoring on my clothes so that I can do it. And tomorrow I want to have this step counter and to calculate the energy I spend every day. And so I can do another one on my shirt. And maybe next time I want to control a robotics. So then I have a EMG sensor on my arm so that I can do it. So then the fourth day, I don't want all these things. Then I can quickly use the scissors to cut them out, and still I have my original shirt. Here is the whole project, the idea of this embroidered electronics. We want to make it flexible, and we want to enable it for the daily monitoring. Okay, so how can we do that? So when we want to do wearable electronics, there are some major components we need to consider. The first one is the sensor design, means what type of signal we want to detect. For example, the ECG or EEG, or it is the application we want for the wearable electronics. And the next one is the contact condition. Contact condition means, okay, so we can use it on our skin, or we don't want it to be on our skin. And wireless communication. Okay, so here we have our ECG. So do we want to have the real-time data shown on the screen? If we do, we probably need a Bluetooth. If we don't, and we can do data storage on the device itself. So that is the wireless communication. And also the power and energy, which is one of the reasons preventing me to really use it every day. Okay, and the next one is the standard and integration. So finally, how we're going to achieve it, how we're going to implement it. Okay, so the sensing include there are a lot of different signals we want to detect. Okay, so here are some examples. So we can do, actually in my group, we can do electrophysiological sensing, which is the ECG, EMG, and acceleration, and which is to show the daily activity and also the temperature. And for the contact, we can do regular contact. We can also do the non-contact sensing, which I just showed. Okay, and for the final implementation, and we choose the embedded system because it's kind of easy to really build things together. Okay, and then to really achieve these nice shirts on our body, we have some challenges. I call it technical challenges we really need to solve. And this first one is motion artifacts. So for example, when I use my Fitbit or some like other type of wearable technology, when we really test it, sometimes when the subjects, for example, myself, I'm doing a large motion, for example, I wave my body, and then the signal is not accurate. For example, my heart rate, you can tell, okay, your heart rate now is 220, for example. That beats per minute, and definitely that is not accurate. Kind of like
let's hope not.
And so this phenomenon is common, and this is called motion artifacts. The reason is that, okay, so when we have these electrodes on our body, and when we are moving, and the interface is changing. So apparently there is uncertainty of the interface. Mm-hmm. And also so for example, I'm sitting in my office and I have all these power lines. Okay, so these power lines gonna cause the power line interference as well. So for all of these noise, normally in a medical device, what we do is we have a driven right leg circuit, which means, okay, so for example, when we do the ECG testing in the hospital, we kind of have a 12-lead electronic system. And people, if you have experience about that, you will see that there are a lot of wires on the body. Okay, but for wearable devices, we don't want that to happen. So what we will face is a more challenging human interface. Okay, and so this is what we're solving so that we can achieve the non-contact sensing. And another thing is, and for this uncertainty of the interface, it has been recognized in the field for a long time, and apparently there are motion artifacts, and in the people that are trying to solve it. But still, there's still, for example, the consumer electronics we bought, and they still have these kind of phenomenon. And there could be a second factor causing this motion artifacts, which is triboelectricity. So what is that? So triboelectricity, when we learn it in high school, that we have two materials. So for example, the fur and a glass, for example, when they really rubber each other, and what will happen? They're going to be charged on the surface of the material, right? And this is called triboelectricity. So
it's called, what is it called?
It's called triboelectricity.
Tribo.
Yeah.
Where? The word where, right? No, I get it. Okay. Yes.
Or, yep. So actually we find that on clothes, especially wearable electronics, this phenomenon really matters. Means it causes these high inaccuracy of the signal. So for example, here I have a video showing how large the electricity can be. And we just use two material, and we just do contact and separation. And we can power all these LED array, all these LEDs. Okay, and we make it as a shape of MTU. Okay, so we just want to show that this electricity is also a leading factor of motion artifacts. So which actually our group proposed it, and we also approve it.
Well, and so to translate a little bit, so tribo, which refers to where, right? By rubbing things together, you can generate static charge, because I think in high school and stuff, we refer to this as static electricity. It's probably not the technical term that you're referring to, but we're all pretty familiar with static electricity, where you touch the tip of your dog's nose and you give them a shock, that kind of thing.
Yeah, exactly the same thing. Yep, so this static electricity, it caused the peaks in the ECG detection and also other type of human vital signal detection. So it's kind of, it really matters. So we want to solve it, we want to remove it, and so that we can have a clear ECG signal for either clinical diagnoses or for daily monitoring, so that you can have an accurate heartbeat. Okay, heartbeat sensing. Okay, so then why we can detect it, why we can do non-contact sensing outside the clothes for these embroidered electronics. The reason is that when we really do non-contact sensing, we need to think about the skin electrode interface. Okay, so here is the upper body and here is the heartbeat. And between the heart and the sensor, there are multiple layers. And we have the skin layer, we have the cloth layer, and we even have air in between. So each layer can be modeled as a resistor and a capacitor. They're kind of parallel to each other. And if we do a quick mathematical modeling, and we can calculate the skin electrode impedance. So for non-contact sensing, this impedance is pretty low, so that it caused some difficulty in the electronics design, which that we understand it and then we solve it. This is one of the challenges we do. Okay, so after solving that, and we have some prototype, which we show the photo in the slide. And this slide shows the results. So these are the ECG signals detected by our devices through 19 layers of cloth. So we try different cloth, and we can see that, okay, so here this is a raw data, and we do the sensing through the cotton and through the jeans, and we also do the polyester and polyester blend, and we try different materials. So we can see that, okay, so with a careful design of the wearable electronics, we can still get the ECG through different types of cloth. And that is the first challenge we're solving. And then after a filtering, so we can have a clear ECG, this is exactly what we want.
Whose heart is this?
Mine. So actually, when I did with this testing with one of my graduate students, and my heart rate, I mean, the amplitude is pretty low, and his was pretty high. And I said, okay, so I may need to do more exercise.
No, having a low heart rate, I think, is a good thing. I don't think it's a bad thing.
Okay. Okay, and then it goes to the second challenge, which is the energy and power. Okay, so now we use batteries, and we probably need to do charging like sometimes like maybe 3 days, I mean, once per 3 days, or say once per day. And how about we have some energy harvesters so that we can have this power from ambient environment. So that means we don't need to really charge it. Say we even don't need the batteries. We can have the power all the time. So how we can make it happen? So we can have, to power these wearable electronics, there are some power resources we can use from the ambient environment. So one thing is the human motion. And definitely we have these devices, and we're moving and we're doing, I mean, activities every day. And these are energies. We can generate the electronics. We can generate the electricity so that to power the electronics. So to convert motion energy, what we normally use is the piezoelectric and electromagnetic and the electrostatics. And because of these motion artifacts, we saw the video, and the electricity was pretty high. So how about we convert these harmful motion artifacts to energy harvesting, so that we can use these static electricity and these charge we don't want, and we use these charge, we collect it, and then we use them to power the electronics. So this is what we do. Okay. So here are some examples, and by using these triboelectricity, and we design some stuff, and this is one example, which is to monitor the gate. Okay, when people are moving and when we're walking, for example, and the gait really tells some health indicators. So for this device, and we call it TriboWalk, so that we put it on the sole and we can monitor the gait of human when they're walking. Okay, and we use this triboelectricity instead of the previous pressure sensing or or maybe other like like piezoelectric materials. So the reason is this triboelectric material is super low cost, and we can also do sensing and energy harvesting at the same time. So it means we don't need the battery at all.
So you're kind of doing the opposite of you know, the sneakers you can buy for children where they're jumping all around and the sneakers are lighting up because it's taking the motion and turning it into electricity and making a light up. You're doing the opposite. You're taking the energy of the person's motion and turning it into electricity to be a monitoring device.
Yep, we can do, one side is that we can do a monitoring device, and the other side is we can use as a power resources, like regular, I mean, the lighting up shoes. Like
I never let my son get those shoes, by the way. He never got the light up shoes, no.
Yep, my son has some. Okay. So the third challenge I'm going to talk about is, we call it ubiquitous sensing, which means, okay, so we have these health monitor. For example, in hospital standard, we call it Holter. There means we need 3 leads, means 3 electrodes, and we need to do the skin preparation so that we need a conductive gel on the electrode, and then we attach it to our skin. But okay, so when patients, when they're sleeping or when they're doing their regular activity, we cannot do 24/7 monitoring. So how about we have some devices that is on our clothes and we can still monitor these vital signals. And for this thing, we call it ubiquitous sensing because we want to achieve everything that won't disturb people's daily activities. Okay, so what that is comes to the next shirt, which is the embroidered electronics. Okay, so to do it, the first thing is we want to make sure everything works. And the second thing is we want to achieve mass production. Means, okay, we want to build up a cloud manufacturing framework so that a lot of people can be involved in this project. And one side, we promote the technology. The other side, we hope that the manufacturers can be involved as well so that we do embroidery for customers. And we also do the device design for customers. So this framework, and we have a website for that. Can I show it?
Yep.
So let me show the website, and which is here. Okay, can you see that?
Yep.
Okay, so this is our Wearable Electronics factory. We called it WEF. And in this factory, and we hope that we can have manufacturers connected as well. So far, we are establishing it. And so here we have a library, and here we have the ECG, and we have the GSR, we have LED arrays for lighting up. And customers say, and you can use this, the link to log into, to see the website as well. And for example, I click the ECG, and I can click download EXP, and the EXP is a machine readable code. So if you have a digital embroidery machine, and you can do it yourself, and just load this EXP file to your own embroidery machine, and you can quickly have your ECG monitor. Okay.
Wait, and so I have to ask the obvious question. So it's through an mtu.edu site. So is this funding your lab?
This is not the website of my lab, and this is, actually IT kindly gave us a small space, not really small, a big space actually, so that we can have a space in the MTU server, and I really appreciate that.
No, that's pretty cool. That's pretty cool. So we could design and build our own shirt or something.
Yeah, exactly. And say, and the function I want to mention is, okay, say if you are not satisfied with our design, and you can design your own, okay? So just, and we have a backend tool as well. So just upload your file and choose the file you want to do for your clothes. And for example, this one, I choose this as an example, okay? And I upload it and I click run. Okay, and we wait for like 1 minute, and there's gonna be an EXP file. EXP file is a machine readable code. Okay, successful. Okay, so you can see that this is the stitches you can use. Okay, just click download, and you will have, you can use our tool to convert the design to manufacturing. So that's why we called it cloud manufacturing. Okay, so let me go back to the yard sale, okay, right here. Okay. Gonna share screen. Okay, and you can use this website. I mean here SOCL, which is short for System on Clothes.me, which is mechanical engineering.mtu.edu, and you can quickly you can play with this tool. Okay, and of course, we also care about if these ECG monitors can work, right? And so here I have a video for this device.
Is this your heart again?
This is not my heart. Okay, so we have this flexible ECG and using the embroidery, and we can see that the ECG is pretty clear, right?
Not bad.
Yeah,
not bad. So, I mean, like this is kind of like a t-shirt against your chest.
Yes, you can do that. You can do that, or you can use your fingers. So it means where the sensor is. The sensor can be on the fingers, and means you can still have the ECG, and which is the arm ECG, and or you can place it on the chest so that you can have the chest lead ECG.
Oh, very cool. Very cool.
And the next thing is, okay, so this is the digitized the stitch generation, which demonstrate how the back end of the cloud manufacturing website works. So we built the software, kind of the software, so that we can achieve the design to manufacturing translation. So here is a short video visualizing the stitch generation using the code. So here we just build a SOCL, and which is short for System on Clothes, which is the logo of our project. And then we can do the embroidery. Okay, so I'm gonna conclude my presentation today. And I would say that today, I wanna just show the stuff we're building, and we're doing the yard sale. So if you're interested in anything, and just contact me. And my email is funny. My email is yes@mtu.edu. And if you have any questions, or if you are interested in the devices we have, or if you are looking for collaborations, or if you are interested in the research or in working in my lab, and we're always welcoming students to work in our lab.
And so did you want to introduce George to talk a little bit about the soft robotics piece?
Yes, so George, do you want to talk a little bit about the soft robotics? So actually for all the things we're talking about in this part is that we're doing sensing. And then now we want to do one step further, which is the soft robotics. And we're trying to use the wearable electronics as the interface to control robotics. But now we're we're just starting the project. So George, do you want to show the video?
And just as a little bit of deep background, so Dr. Sarah Sun is a faculty member in mechanical engineering. George is working in her group. He's also earning a Master of Science degree in mechatronics. So he's a PhD student, and his area of research is soft robotics. And so I think, Sarah, you're going to want to stop sharing, and then
Okay, sure.
George can. Yeah. Oh, and of course, this is a question you never ask a PhD student, which is when are you going to graduate? 2012 maybe, or, you know, yeah. All right, so we are seeing George's screen now. All right, and so go ahead, George.
Okay, yeah, so can everyone hear me? Can you guys hear me?
Yes.
Okay, so for us to start, we need to know what soft robotics is. So basically, soft robotics, what it involves is the design and construction of robots using flexible and compliant materials, which imitates living organisms. So for example, if you have like the octopus, which is kind of flexible, so we'll have some materials that can exhibit in non-linear properties, which can imitate the movement of the octopus, probably the hands wrapping around and stuff like that. So that is basically what our soft robotics is all about. So then why do we want to venture into soft robotics? So the robots traditionally, they are using situations where they don't have face-to-face or close interactions with human beings or with workers. For example, when we are working in an assembly line, where we have rigid robots, if they kind of come close or very close to workers, they tend to exert enough force which might crush the worker. So if we use soft robotics, we kind of eliminate that kind of situation. So my research on soft robotics will be showing two demonstrations. One is on pneumatic artificial muscles, and the other one is on soft gripper. So this demonstration I would display would go for like 3 minutes and some seconds. So I would start that right now. Hello, my name is George Ochieze, and welcome to the Human Capacity Laboratory at the Mechanical Engineering Michigan Technological University. I'm here to make a presentation on how the McGibbon artificial pneumatic muscle can be applied to the field of soft robotics. What do we have here? At the right hand corner, we have a red 12-volt compression pump with a rating of 120 volts, and with this, air is supplied to the pneumatic muscle and produces a displacement due to contraction of the muscle. We will be using this support stack to assist the muscle, so we have a visual inspection of what is happening. As always, safety first. This device can go up to 106 psi, but for this demonstration, we'll be using 30 psi. Okay, so first I'll have to set this 30 psi. And then I'll start. All right, let's see that one more time. Okay, let me just go one more time. One of the major purposes of that application can provide support and by aiding the language.
Nice office, George.
Also, in the use of soft robotics, where the soft paper is used as a mimicry of a human finger. Here, I have the soft paper, which is white in color and a black base, an empty can, and a hand pump. The hand pump supplies air through the air hose, thereby activating the soft paper, which has enough force to break the can. again, we would display this soft gripper the way you that even under gravity, they can't easily tell it.
I think you're trying to kill the Diet Coke can.
Yeah, it's empty.
We can't hear you. You're gonna have to say it louder, George.
Oh, okay. So, okay, I'll explain more with the other slides. So basically this pneumatic artificial muzzle was the first one which I presented in the demonstration. Okay, so but basically these actuators, they are used to contract, they are used for contraction when pressurized air are distributed into the system. So for these pneumatic artificial muzzles, they kind of have different types, but the basic ones are the McKibbins, which is a rubber tube and a textile mesh. So this rubber tube is enclosed in this textile mesh. How does this work? So upon radial expansion of this rubber tube, the textile mesh tends to contract. If you notice, when I was
It's
showing
like
the
a Chinese
demonstration,
finger pull, right?
yeah, so something like that. So when the demonstration was being shown, you notice that when the air was introduced, which is around 30 psi, the muzzle kind of expanded radially. But because it was confined with this textile mesh, there was kind of a contraction, which generates enough force to compress or decompress or twist or untwist a particular application point. So where is this potential application? So generally in the whole world, there is about 41 million heart failures, um, which is found out every year, and around 5 million here in the US, which costs a total of around $30.2 billion a year to cater for heart failures. Why do we have heart failures? Probably because there is no sufficient blood flow from the heart to different part of the bodies. But this can be corrected by the use of cardiac ventricular assist devices, which is part of use of pneumatic artificial muscles. So what we have here is a sleeve with a pneumatic muzzle. So we have three patterns here. The first one is the circumferential pattern. The second one is the helical pattern. And the third one is a combination of both the circumferential and the helical pattern. So how does this work? If we have a pneumatic muzzle, remember when we applied pressurized air into the system, it kind of contracted, right? So if we have this wrapped around in the sleeve and we apply pressurized air into the system, it kind of contracts this apex part of the heart. And when it does that, blood is being pumped from the heart, which flows down to the whole system. So the design depends on probably which part of the heart that needs more pressure to be applied for blood to be circulated more. So we have this, which is the circumferential part, which compresses and decompresses. This is how it works on the compression and decompression. But for this helical pattern, the mode of actuation is twisting and untwisting. So probably these ones are basically used when the person has an issue with the right ventricle. And this is used when the person has both issues with the right and left ventricle. So this is basically the potential application for pneumatic artificial muscles. We still have the second one, which I showed, which is the soft
Very interesting.
gripper. Yeah, the soft gripper is being applied in the industry. But however, this is the design of the pneumatic artificial muzzle, which I demonstrated. This is where the air flows in from. This is a point which is being held in place, so there won't be an escape. There won't the pressurized air won't escape. Then this other end is being held in place, and this is where the load is being attached to. Okay, so this is where the rubber tube is being enclosed inside the textile mesh. So this is where the constriction and relaxation occurs. Then for the second one, which is
Sorry.
All right, it's getting way too
Reminder.
technical. I'm pulling us out. I'm pulling us out. We're gonna ask some questions now. So George, I'm very interested in having you back on Husky Bites in about a year and a half when we can see how you are somehow plugging in a compressor to a human heart and making these things do something cool, or applying it to a robot. But I did not know anything about pneumatic artificial muscles, so thank you for that. And very, very, very interesting. So we have a few questions. The first question is from Todd. So by the way, you can ask questions anytime you want. We will continue answering questions until we're finished with questions, or until it's like 7:20, so that we can kind of close it up. We have about 4 or 5 questions kind of out there. And all of you who joined us tonight, thank you so much. It's been wonderful to be here with you. So again, we have Dr. Sarah Sun, mechanical engineering mechanics faculty member at Michigan Tech, and George Ochieze, who is one of her PhD students studying pneumatic artificial muscles and soft robotics and more as a PhD student. All right, so the first question is from Todd. What is ECG short for?
ECG is for, ECG monitors the heart rate, and which shows the QRS shape, which is when we
Electrocardiogram.
Yes.
yeah.
And so that's the little that you were showing us, right? The little plot that you were showing us as a function of time, which is, I don't know the words, but like there's a peak and a trough and then a jiggle and then it starts again, and that's your heart. So that's your.
Yep, so this is P wave and QRS and T wave, which is one beat of a heartbeat.
No, very good. Thank you, Todd. Bill asks, is there going to be a replay of this presentation? And so for anybody out in the audience, so just go to mtu.edu/Husky Bites, and you're going to see all of the summer's presentations. This presentation will be posted within about 24 hours. Yeah, they'll be up there, and you can send it to your son or daughter or grandson or granddaughter if they're interested in this subject. You can send them the link, and we hope that you do that, because the whole point was to learn something new, and I learned something new for sure. All right, and so this is from another attendee who asks, is it possible to share my design with others on your website? For example, if I find out my design is pretty useful and I am sure it will be helpful for others in the community, I want to be able to share my design.
Yeah, definitely, yes. And we have the library, and the library is open to not only the research community, actually is open to everyone. And if you feel that, your design is great and you already tested and it works, and definitely contact me and we can add your design to the library so that others, they can download it.
No, very, very cool. And this next question is for George. What do you see as the major obstacles to using a pneumatic artificial muscle kind of in the human body?
So the major obstacle is to contain the air pressure, because there is always leakages. So the issue I always have is to contain this pressurized air to keep it in place so it could work the way I want. Because
So
I have done a lot of, sorry?
So it doesn't explode your vein or artery?
Yeah, exactly. So I've carried out some of my projects which didn't work out the way I wanted, because there are so many air leakages, and when you pressurize so much air leakage, it doesn't work out the way you expect it to sometimes. So the major problem is controlling the amount of air into the system.
Interesting. Switch to hydraulics, I think. Switch to hydraulics. Maybe it takes less pressure. I don't know. This is why I got out of chemical engineering. All the pressure stuff, I was just like, oh, I can't think about this anymore. And and I ended up in material science. All right, and so we have answered that question. And this next question is for Dr. Sun. Could someone who owns a newer digital sewing machine, one that you could buy at Walmart, for instance, use the code to create an ECG heart monitor? If so, once it is embroidered on the cloth, and I place the embroidered cloth over my heart, how do I see the results?
Yep. So actually, if you take a look at the socil.me.mtu.edu, if you download the EXP under the ECG, and that one we already tested and we showed it in the video that it works. So if you download the code and you do the embroidery on your machine, an additional embroidery machine you have, and then you're gonna have this thing. And then what we need to do is we still need to do a little bit soldering so that we can have the IC, and which is this off-the-shelf integrated circuit. We need to have the small IC soldered on this part. And also our group is developing the embroidered capacitors and resistors so that we don't need to do further of the soldering of other components. So for the EXP, and once you have the thing, and you can place it on the left chest, which is right here, left right here. Okay, and even on the right, and you can still have your ECG, but the shape is not the typical QRS shape you want. And if it is on the left chest, you're gonna have this QRS, which is like beat by beat ECG. And then for the sensing and the sensor, if we do, for example, we place the, say you have my shirt, you have your shirt, and then you do the embroidery here, for example, and yes, it can work. And say further for finally what you want to see the data, which is your ECG. Okay, there are two options. The first option is we cannot really see that. We save it on board, means all the data is saved on either a memory or something like that. And so that after a few hours, and you can pull out the data, use your computer, and then you can plot it. But you cannot really see the signal real time. And the second option is we can connect a Bluetooth module, which is a wireless communication module. And in that case, this embroidered electronics can be wirelessly communicate the data to either your laptop or your phone so that you can see the heart rate in the real time. Okay, so there are two options.
Very nice. All right, this next question, so this is a compliment from John, thanking you both for the presentations, which were excellent and interesting. Thank you. And then the next
thank you.
Question is from the same person. Is the library open source?
The library, yes, it is open source. And even the whole website is actually open source. I mean, the design to manufacturing translation.
No, that's good. That fits in nicely with what we were talking about in the first week of this fall series. All right, so this is from another one of our attendees, Dr. Sun and George. Thank you for your presentations tonight. Is all of your research biomedical, and are there other applications in other areas of engineering?
They're not necessary to be biomedical, although our initial goal was biomedical. So our initial goal was for health monitoring. So we were doing wearable electronics initially was for human-centered healthcare. And then we find out, okay, so these signals can be used for other applications as well. So for example, for the second poll we did was the driver fatigue thing. So for example, these wearable embroidered electronics, they can be done on the safety belt, for example, so that we can monitor the driver's state. And there could be other applications. So that's why I say that everything's on sale today. So if you think of other applications, or if you want to collaborate, and definitely let me know. And we provide the technology. And if you can provide the application, that's great.
Well, and my iWatch, I mean, every now and then it's like tapping me. It like taps me, you know, I feel it did it. And it's like, stand up, for goodness sake, stand up or you're going to die. And, you know, it doesn't say it like that, but it basically it realizes I've been sitting for way too long and it wants me to stand up and walk around. And it's kind of useful to be tapped, you know, it's kind of like, whoa, I guess it's 3 hours in a row. So, all right, the next question is for you, Professor Sun. Do you have undergraduate researchers who work in your lab? And if so, which majors are best for this field of wearable electronics?
Yes, definitely. We accept undergraduate research assistants in our lab. And I'm very happy if undergraduate students are interested in the research and interested to participate in the research. The best major, I would say that we're kind of interdisciplinary. So we have students from electrical, previously we had students from electrical engineering, mechanical engineering, and one was from computer science. So probably these 3 majors. Or if you're from other engineering and you are really interested in the project, and we can discuss as well. And just if you feel that you're interested, you can send me an email and we may schedule time to discuss about it.
Well, and conveniently, Dr. Sarah Sun's email is just yes, Y-E-S, at mtu.edu. So it's pretty easy to remember her email address. And I don't know how you got this very lucky email, but yeah, I bet a lot of people are jealous of your email. So we are at 7 o'clock on the hour. At 7 o'clock, I just always like to thank both of our, first of our featured speaker, and secondly, co-host George. George, you are our first graduate student to have on the show. I think you are. We've had graduated graduate students, but no actual graduate students. So it took a lot of courage to come up on here and to be with your advisor answering tough questions. So thank you so much. It was nice to learn about your research. Dr. Sun, thank you for telling us about this whole new field of wearable electronics. And so if anyone was joining us for the first time, this is something we're doing every Monday night at 6 p.m. EST. We have kind of conversation at 5:45 between the co-host and the speaker. And it's an educational piece, it's family friendly, so feel free to invite others, to join others, to send the links to friends. We're gonna take the time to answer the next questions. We've got about 6 open questions remaining. Thank you again, attendees. So this question is for George. I was curious about this too. What is the grip strength of the soft robot hand, you know, that tried to squish the Diet Coke can? Do you have any idea what kind of strength range it had?
So for the one I developed, the strength is around 50 newtons. But it can be easily calculated because pressure is kind of relative to force, right? With respect to the area which is being applied, right? So if you have the area of the soft gripper and you kind of introduce 30 psi, it's kind of easy to calculate. So it is more like a straightforward calculation. It's just very simple. But for that soft gripper which I demonstrated, it's a force which was exerted is 50 newtons.
So the one that did that, was that one of the twisted fabrics?
No, the soft robotics, the soft gripper, which is the second demonstration.
Okay. No, and I'm sorry I kind of cut you off on that, but it was getting hard to hear, so I think it was better to go to kind of live. All right, so this question is from another one of our attendees. How does laundry affect the functionality of the embroidered sensor? So when you put your little shirt or whatever through the laundry, does it come out as a pile of wires, or what happens?
That is a good question. So actually that is one of our testing experiments. So we want to see how many loads of washing and drying load, so that, I mean, these embroidered electronics can last. So in our previous testing, it was about 20 loads, so that we can still have the circuits working. And more than that, it's hard to say. There is a percentage of after 20 loads and 20 cycles of loads, and how many electronics, what is the percentage of the wearable electronics they will work.
Yeah, I mean, I'm not sure how long our jeans work after that many washes either, but so the next question is from Dr. Archer, who is the chair of electrical and computer engineering. How do you solder these devices to the fabric? How do you make the electrical connection?
We have the conductive pad for the IC so that we can do the soldering.
Say that again?
We have these electrical pad, so we can see that these are the pad. When we make the pattern, and we make the pattern as well, so that we can do the soldering.
Okay, so you kind of sew it right onto something that already makes the contact?
Yes.
Okay, there you go, Glenn. All right, so this is another question from the person who asked about the washing, who is suggesting why use pneumatics, which is air pressure, instead of hydraulics. And didn't I mention that to you too? I know nothing about either one, but I'm pretty sure hydraulics would be better. So you're gonna have to think about that, George.
Yeah, so it's quite easy, right? So hydraulics is, mainly basically on the flow of fluids, right? And we are considering pressure. We're not considering flow.
It's
So
fluid versus air. Yeah.
yeah, so it's very easy.
And fluids are less compressible, so it takes
yeah,
less
less
force.
compressible. And another thing is in the medical field, it's quite advisable to use air because the hydraulics can easily contaminate with the blood and really cause a lot of damage to the system.
Well, we think you should explore hydraulics. All right, so John asks. Well, I don't know, really. There's two of us who know nothing about the field, and you look at you. You're going to be. So remember, what you are at the time you earn your PhD, George, you will be the world's expert in your field of study. You will actually be the world's expert in your field of study, and so.
Exactly, you will know more than me.
And you're close to that now. I mean, and so that's the whole point of the whole doctoral degree. You end up becoming the world's expert in this. And it becomes very focused, right? But you end up actually being able to you've read all, because if you haven't read all the stuff, somebody's going to ask you a tough question. But doing all kinds of reading about this kind of thing, and remember, honestly, I swear, getting a PhD was easier than getting my bachelor's degree because I liked the focus. I liked being kind of like narrowing down instead of having to think about 1,000 things. I could only think about the things that brought my research forward. All right, so this question is from John. What kinds of companies are hiring your graduates, Sarah?
So actually, my previous PhD students, they went to academia.
Into academia, okay.
Now a postdoc at the University of Pennsylvania. And actually, they didn't really look for industrial jobs, so I'm not exactly sure.
No, well, it must, I know you've done a really good job of bringing in external funding from the National Science Foundation in support of your work. This is a really growing area, an important area. Just last week, I bought an oxygen sensor for my finger because we were both scratching our heads, wondering if we had COVID. And I'm like, all right, I can solve this with $25. I can buy a fingertip sensor and I can have it in my drawer. So next time we imagine we have COVID, we can measure our oxygenation without going to the hospital, and, neither of us had COVID, but it was awfully nice to have that sensor. I feel kind of comforted by having that sensor in the drawer. It's kind of like having a thermometer. I have an oxygen sensor. I have an EKG. I've got everything I need to kind of decide if I have a problem at home at this point. All right, this is from Anonymous. So this is to Sarah. Do you expect this technology is safe for children, even babies or newborns with heart issues?
Yes. One applications we're currently doing is for infant monitoring, and because for all of these, they're fully fabric, and the current, the electricity is very low, and it's safe and it's soft. So I would say that yes, it's safe.
No, that's really good. This is really good. All right, and so we have one more question. We've answered 15 questions. We have one question remaining right now. This is to George. How did you first learn about soft robotics? Is it a growing trend in robotics? will it play a big role in manufacturing in the future, or do you think the applications are mainly medical?
Oh, okay. Prof. Dr. Sarah Son kind of introduced me to the field of soft robotics. That was the very first time I learned about it. And yes, it is a growing field. It is a growing field, not just in the medical industry, but also in the manufacturing industry. Actually, my PowerPoint presentation has another clip which shows soft robotics used in the manufacturing industry, probably in where some of these packaged foods are made and clothes and stuff like that. Yeah, not just in the medical field. It's a worldwide kind of application robotics part.
Yep,
And
it's
you,
kind of like an emerging field. So although the technologies, I would say they're not really mature right now. And so it's still, there are some steps to go to really make it mature for the real applications.
well, and I think we should probably close this. We've been kind of circling around graduate education across this topic. Maybe um, kind of first, George, what advice do you have for people who are enrolled in a doctoral program? What advice do you have? And then Sarah, it's the same question. What advice do you have for people enrolled in a doctoral degree program? Because you know, you don't really, anyway, I'm just going to leave it up to you to kind of give some advice, because sometimes you're in the doldrums and you're like, I'll never get done. I'll never get done.
So for me, I think the first thing you have to know is that you need to have interest in your project, because if you're not interested in your project, it will be very difficult for you to grow. And secondly, you should be honest with your supervisor and try to give your supervisor feedback. If you have any issue, just try to give your advice or the feedback. This is what I have. This is where I'm stuck. Just honesty, interest, and hard work.
Bravo, bravo. Dr. Sun.
Yeah, George is doing great. He is a wonderful graduate student, and I would say the same. And yes, so for graduate study, I would say that is like 4 years or 3 years or 4 years you're doing one thing. So my suggestion is that you may need to be interested in the project, and you may be passionate about the research you will do.
No, I agree. I agree. If it's not interesting, it's pretty hard to make yourself do it, and so
Yeah.
that's always been true. That's a truism, I think, across all fields. So it's hard to go to work if you don't love your job. So it's nice to know that you guys both like your jobs and love your jobs, and I sure love my job. So I want to thank you from the bottom of my heart for being the first graduate student to be a co-host, and Sarah for sharing about your brilliant research. And thank you, everyone. Thank you, everyone, for attending Husky Bites, and we'll see you next. Wait. I have another slide to show you. Hang on. Let's see, I have to share my screen, and I'm gonna try not to show. All right, so sorry, I'm showing you my mechanical engineering alumnus who's wearing his Husky Bites t-shirt. So we give prizes for good attendance, by the way. And so if you have a passing grade, you will get a nice prize like a t-shirt or something like that. And so I do want to give a plug for the next week's Husky Bites, which will feature Orhan Soykan, who's going to talk about prolific inventing. He is a faculty member in our Department of Biomedical Engineering. Co-host alumnus Tim Kolazar, who graduated with a biomedical engineering degree in 2019, and who works at Abbott Labs, will be the co-host. And I do want to once again acknowledge tonight's sponsor, which is Darwin and Margarita Moon, who sponsored tonight's really important topic on wearable sensors for health monitoring. And thank you, everyone. We've had our Q&A, and if you are interested in sponsoring, all you have to do is send an email to, let's see if I have the email somewhere. I think it's engineering@mtu.edu. So good night, everyone, and thank you so much, Sarah and George, for your time tonight, and thank you, everyone, for joining us.
Okay, thank you so much.
You're welcome.
I
It
was
was wonderful.
kind of surprised my parents joined.
Who has joined?
My parents.
Your parents are online, and
Yeah.
Oh,
that's a long way from here, right?
And they did ask a couple of questions.
Do you want to tell them a special message?
Oh, okay.
For joining
Yeah,
us from
I'll
Nigeria.
just say thank you for supporting me so far. I mean, that's been really been tough for me, but they've always been there. I'm really, really grateful for that.
Well,
okay,
we're very proud to have you here, George. And so thank you, George's parents, for sending him here.
George is doing excellent.